Today we'll be looking at lesson 1.07, what comes next, what comes later. Our objective today is, I can write the missing terms of an arithmetic sequence in 2 out of 2 problems. So we've looked at arithmetic sequences so far, but now we're going to fill in some more missing terms than we've had before. And here's some things to think about. How can you find patterns when multiple steps are missing? Are there things we know about patterns that we can apply to ones that have missing steps already? Okay, so first, what tools can we use to model sequences? Can you think of any that we've used up to this point? Let's see, we've had graphs. Whoops. We've had graphs, tables, equations. We've also used pictures. And we've even used stories. All of these things can help us model sequences. So maybe we'll use multiple of these tools to help us solve some problems. Okay, first problem here. How would you find the missing term in this arithmetic sequence? So this is just one missing term. We've kind of seen this before. There might be a few ways you might try to solve this, like you could try to guess and check. So maybe this looks like, maybe we could add 4. Maybe that would work. We get 9. But then here we would get 13, and that's wrong. So that one didn't work. And then we might say, well, maybe it's 3 because 4 was too big. So maybe we'll try 3. We get 8. Add 3 there, and we get 11. So guessing and checking did work for us that time. Although if our numbers get really big or are not integers or something like that, guessing and checking might not be the most efficient thing to do. Can you think of other ways we might find missing terms here? One of the things we can do is we can look at the difference between these two numbers and then divide it by the number of steps to get there. So let's look at that. If I take the difference, which would just be 1 minus the other, so 11 minus 5 equals 6, that's our difference. And then I look at the number of steps it takes to get there. There's 1 step and 2 steps. And since we're adding the same thing at both steps, we're going to divide this difference by the number of steps. Difference divided by steps equals 3. So we would add 3 at each step. So here's another example. Find the missing terms in this arithmetic sequence. And can we use the same method as before? Well, the guess and check might be trickier this time. Looks like it's going down, so we'll probably choose a negative number. But other than that, I might just try this other method where we find the difference and then we divide by the number of steps. I'll just write that up here. We find the difference divided by number of steps. So let's see, our difference here, we have negative 10 minus 18. And that simplifies to negative 28. And then our number of steps here is 1, 2, 3, 4 steps. So negative 28 divided by 4 is negative 7. And notice that does match up with what we figured out before, that this should be a negative number since this is going down. So if we subtract 7, we get 11, then 4, then negative 3, and then 10. Another way you could think about this, if you're really inclined toward algebra, And just delete all of this, all of it. There we go. Is we can look at this sequence and say, we are adding the same thing at each step here. And we could put a variable on that. We could call it, say, C for common difference. So we're adding C, C, C every time. So what does that tell us? It tells us that we start with 18, we add C 4 times, and we get negative 10. If we put that into an equation, we get 18 plus 4 C's equals negative 10. And then we could solve that. We subtract 18 from both sides. We get negative 28 over here. Divide by 4 to get C by itself. And we get C equals negative 7. Same answer as we got before. So both of those methods work for us. Here's another one. Find the missing terms for this arithmetic sequence. Go ahead and pause the video, see if you can figure this one out, and then check your answer with me afterward. So we said we needed to find the difference. Remember, this is difference over number of steps. So our difference is going to be 40 minus 10. And our number of steps is 1, 2, 3, 4, 5. Another way to look at the number of steps, is, especially if we have a lot of them, is you could just take the biggest one minus the smallest one. 6 minus 1 is also 5. So 5 steps on the bottom. 40 minus 10 is 30 over 5. So our step here is going to be positive 6. You can see we are going up, so it makes sense that this should be positive. Add 6 each time. And we get to 40. All right, now we're going to add a step on here. Find the missing terms for this arithmetic sequence and then write an equation. Okay. So, once again, we have our difference over number of steps. Our difference is going to be this one minus this one, so negative 6 minus 12. And our number of steps is going to be 7 minus 1. Now, what if you get this order wrong? What if you did 12 minus negative 6 instead? What would happen? It's actually okay to do that. What you'll get is the negative number of what you're looking for. So you just need to be aware whether this sequence is increasing or decreasing, and then make the negative sign applicable. So negative 6 minus 12 is negative 18. 7 minus 1 is 6. And negative 18 divided by 6 is negative 3. So that's our step. At each one is negative 3. That's our common difference. Negative 3, negative 3. We have 9, 6, 3, 0, and negative 3. All right, so what is our equation now? Do we remember how to write an equation? Well, we had our good old friend Slope-Intercept Form. This is what we use for arithmetic sequences, mx plus b. M is the common difference. And b is our value at 0. Notice up here we don't have a 0 step. We have to go back one. So if we go back a step, we have a 0 here. And then this would be 3 bigger, so this is going to be 15. Our value at 0 is going to be 15. So our common difference is -3. That's what we got up here at each step. And our value at 0 is 15. So overall, our equation is -3x plus 15. Now there is a shorter way to do this if this makes sense to you. If this doesn't make sense to you, just forget I ever said anything. But if you want to use this number, the value for 1, you can actually use x minus 1 in your equation instead. Watch how this works. So we'll use our same common difference, but now instead of x, I'm going to put x minus 1 in here and use the value at 1. That is also a valid equation, and is actually equivalent to this equation here. They are the same equation because if you distribute through, you get -3x plus 3 plus 12, and 3 plus 12 is 15. So these are equivalent equations. If this made sense to you, how to use the first value, that's cool. You are welcome to use it, but don't feel like you need to. You can just go back and calculate what the value at 0 is and use that instead. So how would we find the 20th term in that last sequence? We found an equation. Can we use that equation? Let's see, our equation was f of x equals -3x plus 15. Can we use that to calculate the 20th term? Well, we can substitute in 20 for x. -3 times 20 plus 15. That equals -60 plus 15, which is -45. So instead of having to add -3 a whole bunch more times and possibly lose track, we can just use the formula that we derived, or the function that we derived, in order to calculate f of 20. Another thing we could do is we could utilize graphs. Now we haven't looked at graphs in a little bit. And one of the problems here with this graph is that we have too big of numbers for this square. So this square only has 11 lines up and across, and we need to go to at least 20 to get all the x's in. And it looks like the f of x needs to go pretty far negative. So what are we going to do? How do we graph this so that all these things can fit on it? Well, we can count by 2 on the x and then count by 10 on the y. This is called scaling the axis, or scaling the axes in this case, since we're scaling both of them. So let's look at how we do that. First of all, I'm going to draw my axes on here. Maybe I'll put my x-axis right here, and my y-axis right here. Doesn't like to fit right on there, but you get the idea. That's where the y-axis is. So there's our y, here's our x, and instead of counting by 1s now, I'm going to count by 2s on the x. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And on the y-axis, I'm going to count by 10s. You can count by different numbers on the y than on the x, that's okay. So this is going to be 10, 20, 30, 40, and 50, and then we'll go -10, -20. And I just put these axes in this particular place because I knew that our f of x was going to go negative. So now I can just graph these. Let's see, 112 is right about here, right about there. 29 is right about here. 36, maybe right there. 4-3, maybe there. 5-0. And you can see that's kind of forming a straight line, right? Maybe not precisely because it's hard for me to draw exactly where this would go, but a straight line kind of close to that, right? Not quite close to that. There we go. More like that. It's not exactly in this program. It's a little bit wonky, but sort of like that. But that's about as close as we're going to get. But then you can see down here, what is our value at 20? It looks like -45, right? Which is the number we got when we plugged it into the equation as well. So doing it by graph and doing it by equation worked the same. Isn't that cool? It's awesome. And here's just a note that you can count by bigger numbers as well. You see on this graph we're counting by hundreds, 100, 200, 300, 400. And this can be really handy when you're graphing geometric equations because those numbers can get really big really quickly. So let's try another one. What's the 15th term in this arithmetic sequence? How could we find that out? Well, the first way we talked about was to find a formula. And the first thing we needed to do was find out what these missing terms are, find our common difference. So our difference over our number of steps is going to be 18 over 3, which is 6. We're adding 6 each time. 10, 16, 22. Our function will be mx plus b, where m we just decided was 6, and b is our value at 0. So there's 0. We go back 6 and we get -2. So -2 plus 6 equals 4. So b is -2. And overall our equation here is 6x plus -2. To find the 15th term, we can plug that in. Let's do f of 15 equals 6 times 15 plus -2, which is 90 plus -2, which is 88. So once again, we could use graphing to find the 15th term in this arithmetic sequence. We actually don't even need to find these missing terms at all. We could just graph these 2 points and do the straight line between them and see what we get. Now it won't be as precise as our formula, but it might be just fine, it might be enough. So I've sort of got my axes down here. And I'm going to do similar numbering to what I did before. So we'll do 2, 4, 6, 8, 10. And then I'm going to count up by 10s here to make sure we have plenty of room to get to the 15th term. And now I'm just going to graph these 2 points, 1, 4. So if I actually use this as my 0 over here, then 1, 4 will be right about here. And then we have the point 4, 22. So that'll be right about here. And then we can draw a line between those 2 points. Oh, this program is terrible about drawing lines. Let's see, can we get it closer? And maybe this one up here a little bit more? Okay, that's pretty close. So what does it look like 15 is at. This is a really good demonstration of why graphs are a little bit imprecise, especially when we do them by hand. But with 15, it's right about there. The answer we got with the function was 88, so really it would be right about there. Which you can imagine it would be if we actually got the line right where it should be. Just a little bit higher. Okay, last one. What is the 20th term in this arithmetic sequence? Pause the video, see if you can do this on your own, and then I will show you how to do it. So we find the difference over number of steps. Our difference is going to be 4 minus negative 8. Now I'm going to show you the other way. What if we did it in the wrong order? We did negative 8 minus 4. What happens? And then our number of steps is 3. We will get negative 12 over 3, which equals negative 4. But you can see here, these numbers are increasing. These numbers are going up. So it couldn't be a negative 4. We have to intuit this would be a positive 4 instead. So that's the only thing that changes if we do the order wrong. We just need to change the sign. And we can do that based on logic, based on knowing that we need to go up. So this goes up 4, 4, and 4. This would be negative 4, this is 0, this is 4. Our equation is going to be f of x equals mx plus b. M is 4. B is the value at 0. So over here we have 0. Over here we have negative 12. So our equation is going to be 4x plus negative 12. And then f of 20 is 4 times 20 plus negative 12. And that equals 80 plus negative 12, which is 68. So that brings us back to today's objective, which is I can write the missing terms of an arithmetic sequence in 2 out of 2 problems. So that's what we looked at today, finding the intermediate missing terms in an arithmetic sequence, as well as finding terms extending beyond the sequence that we're looking at.